Hello everyone, my name is Peter Giesl and I'm going to talk about approximation of matrix-valued functions with applications to contraction metrics. So this is a talk that combines kernel methods. So I will talk about how to approximate matrix-valued it has a nice application in dynamic systems, namely contraction. I'm going to try to talk about these two topics and how they link together. Let's start with an overview. In the first section, these will be the kernel-based approximation methods, and I'm going to talk about how they work for scalar-valued functions, which is the existing theory, and a new contribution that lifts this to matrix-valued functions. And then as a particular application of that in dynamic systems, we're going to look at contraction metrics. First of all, I'm going to explain what that actually is. It's basically a specific metric with respect to which trajectories of a dynamic system will have a decreasing distance. The distance contracts. And it's a useful technique to find periodic orbits and their basin of attraction, and the same also for equilibrium. And then we basically match these two areas, kernel methods and dynamic systems, and use these methods to construct a contraction metric. Sorry, and I'll show some examples at the end. I should have said it's joint work with Holger Wendland from Bayreuth. Right, so let's start with the kernel-based approximation methods, and let's start with the setting. So we have start first of all with a Hilbert space, a real Hilbert space with an inner product, with a dual we denote by H star with corresponding inner product that I denote by H star, so of all linear and continuous maps from H to R. And then the Ries theorem tells us each element in the dual space lambda has a Ries representer. There's one and only one element of H, so that we can write lambda of F as an inner product of F with this Ries representer V lambda for all F. And we have this relation between two elements of the dual space and the corresponding Ries representers in H. And the definition of an orthonormal basis is that it's orthonormal, that's the first condition here, and that the span is dense in H. Right, so let's look at an optimal recovery problem. And as I said later, or you can see in the examples, the easiest example would be an interpolation problem, but we will later see that also linear PDEs fall into this class. So in a very general setting, we still have the Hilbert space with its dual, and we are given n linearly independent functionals. They could just be the delta functionals, so these would be point evaluations of elements of the Hilbert space, so think about functions, and corresponding values of for these functionals. And the problem of optimal recovery is the following. We're looking for generalized interpolant. So first of all, we need an element S in H, so that lambda I of S are these values Fi. So if lambda I are interpolation values, if lambda I is delta xi, then this is the classical interpolation of function with certain values. This obviously is not unique, so there are lots of interpolants usually for certain data. To make it kind of unique, we want an optimal recovery. We want the element that satisfies these interpolation conditions here, but also minimizes the norm in the Hilbert space. And examples, as I said, if lambda I are delta xi with distinct points, then we have a classical interpolation problem. But we can also choose lambda I to be delta xi after L, where L is a linear differential operator, and evaluate it at certain points, xi, and then this is a linear PDE problem, or we can combine these two, and then we have linear PDE at certain points, and then interpolation problems or boundary values at other points. So it's a combination of these two. So the optimal recovery problem is quite general and covers both interpolation and PDE and PDE boundary value problems as well. Right, so what can we say about solutions for this optimal recovery problem? There's a unique solution of this problem, and it's given by, so S star, the solution of this problem is given by a linear combination with coefficients beta j of Vj, and the Vj's are the Ries representatives of the lambda j's. The lambda j's on the previous slide here that were our given linearly independent functions. So this is just the definition of the Ries representative again. And the beta j can be found by the interpolation condition, yeah, because the S star has to satisfy the interpolation condition lambda I of S star is Fi, and we just plug in this formula and find that lambda I of S star is given by this expression here. And looking at this, we can see that this is nothing else than a system of linear equations for beta, which are our unknown coefficients. Yeah, so the easiest way is to write it down as a matrix. A beta is F. F is the vector of Fi's here, and A is the matrix Aij given by lambda I Vj. And then you can see that this equation here is the equation A beta is F. We can also write this with a Ries representer, and we can see straight away from here that it's a positive definite matrix that includes our, we said that the lambdas are linearly independent. So the solution of this optimal recovery problem is quite easy to establish. It's obtained by solving a system of linear equations. However, to find this matrix A, it would be handy to actually calculate this lambda I Vj or in this form. So it would be nice to have a nice expression for the Ries representatives of the lambda I. So going one step further is we now look at a specific set of Hilbert spaces, namely a reproducing kernel Hilbert space. And the advantage in this context will be that the Ries representatives have a particularly nice form. So this matrix A in the previous slide will be quite easy to calculate. And we're looking basically at this section twice. First of all, we look at the, as I said, all of this is kind of classical theory for scalar valued functions. And then we kind of lift this, and this is a new contribution to matrix valued functions, because that's what we also later need for our application in dynamic systems. So let's start with a domain in RD, and we're looking at the Hilbert space from with functions from omega to R. And such a Hilbert space is called a reproducing kernel Hilbert space, or RKHS. If there is a kernel, the kernel is a map from omega times omega to R with these two properties. So the first property is if we fix one entry of our kernel, x in omega, then as a function of the other entry, it's a function in the Hilbert space. And the other one is the reproducing property. So a function f of x in the Hilbert space can be written as the inner product of f with the kernel. Well, this x is one of the components of phi, and the other one is where we apply the inner product. So that's the definition of a reproducing kernel Hilbert space. We can also start with the kernel. So given the kernel, we look at the linear combination, all finite linear combinations here, and look at the span of these functions. And then we close, we look at the closure of this here, and that will be the reproducing kernel Hilbert space with this unique kernel phi. So when is a Hilbert space of functions a reproducing kernel Hilbert space? There's an alternative way to find out whether that's the case, and it's a reproducing kernel Hilbert space if and only if the Dirac delta distribution is in the dual space. And the proof of the lemma is quite easy. Basically, if this is true, then you can just define the kernel by looking at the Ries representer of right. So if we have the kernel reproducing kernel Hilbert space, then we have certain properties of the kernel. So the kernel can be written in this way. We can also exchange the order of x and y of both components of the kernel. And the property I'm going to prove here is we have a nice expression of the Ries representer. That was the reason I started this section about the reproducing kernel Hilbert space, because remember on the optimal recovery earlier, we needed to find the Ries representer of a lambda. And now, so the Ries representer of lambda is given if we are in a reproducing kernel Hilbert space just by lambda applied to with respect to y. So one of the elements of our kernel to the kernel. So that's still a function of x, and that's the Ries representer. And to see that this is true, we just start from the right-hand side. So we start here using the property of the Ries representer. Yeah, so we can write it lambda y as the inner product of this function here with a Ries representer. We can switch the order in the inner product, and then the last property is the reproducing kernel property, and that establishes this equality. So the matrix earlier that we wanted to compute, the Aij, was lambda I applied to the Ries representer Vj of x. I just put this x here, which means I apply lambda I with respect to x. I mean, at the moment, there's only one variable anyway, but you see that now using this representation of the Ries representer as lambda j with respect to the other variable y, and remember we can exchange these two here, we find this very nice formula for the matrix. So given lambda, our elements of the dual space lambda, in the reproducing kernel Hilbert space, we get this matrix here just by applying lambda with respect to x and then lambda j with respect to y. And that builds our collocation matrix. Right, now for these kernels, the kernel we are going to use today, but that's obviously not the only one that's available, we're going to use so-called Wendland functions because these kernels are compactly supported. They are defined, first of all, as a scalar function, psi. So it's 1 minus r plus, which means the plus just means it's if the argument is positive, it's just the argument. And if it's negative, it's cut off by 0. So it's this polynomial 1 minus r to the power of L, and then they're defined by recursion with respect to the second component by this integration. So the psi is a function of r, and we can use this psi with argument x minus y to have a kernel into these two arguments x and y. So what we see here actually is the function, well, this function I should say, and x minus y is what you see here as argument. So you can see it has a compact support here of 1, the radius of 1 here. And if we use this relation between the two coefficients L and K, where L is defined in this way, we fix a K and then L is given by this expression k plus 1 plus dimension over 2 floor, then this is a kernel. The kernel has a certain smoothness, namely it's a C2k function. K is a natural number, and the corresponding reproducible kernel Hilbert space is not equal, but it's norm equivalent to a Sobolev space, and the Sobolev space is of order k plus d plus 1/2. For all purposes later, we identify the reproducing kernel Hilbert space with this kernel here with a corresponding Sobolev space. Actually, they are just norm equivalent, but that's kind of good enough for our purposes and the error estimates. So just to recap, there's an easy way you can actually explicitly calculate all these functions psi. They actually depend on just the norm. So these are called radial basis functions as well. And they define a kernel of a reproducing kernel Hilbert space, which is norm equivalent to a Sobolev space of a certain order. And there are whole families. So if we increase k, we get smoother and smoother functions. And the other thing to remember on the Wendland function is they're compactly supported. Right. Now, as I said earlier, in the second part of the kernel section, we are now looking at matrix valued functions. So what we want to do now is optimal recovery, as we did earlier, but now the function, so the Hilbert space, is a space of functions from omega into matrix values. So more generally, we just say we want a generalized interpolation of functions from omega to W, where W itself is a Hilbert space. It could be R, then we're back to the previous section. It could be Rn, so vector valued functions, or we are particularly interested in matrix valued functions. So W could be the n times n matrices, or we are actually interested in the symmetric matrices, so the subset of Rn times n of matrices that are symmetric. So we are now looking at generalized interpolation of functions from omega to W, and we have in mind that W will later be mainly the symmetric matrices. And the optimal recovery is basically the same problem. So our Hilbert space is a Hilbert space of functions from omega with values in W. But again, we're given linearly independent functionals in the dual with certain values f1 to fn, and the recovery problem is the same as before. It needs to satisfy this interpolation condition, so lambda I of s is fi, and it minimizes the norm of the Sobolev space. And the solution, because that was the solution in any general Hilbert space, is still a linear combination of the Riesz representatives, and the betas can be found by the interpolation condition. Now, how do we actually solve this? Well, we now need, the first step is to generalize the concept of reproducing kernel Hilbert space from scalar valued functions earlier to matrix valued functions, or general Hilbert space valued functions. And then we're obviously interested in what is actually the Riesz representative of a lambda I. So what's this quantity? Because that's what we need to calculate. So here's the definition of a reproducing kernel Hilbert space in this more general setting. Omega is still a domain RD, but W is now a Hilbert space. Again, we have in mind matrices here. LW is the set of linear and bounded operators from W to W. And the Hilbert space is called a reproducing kernel Hilbert space if we have a kernel. So this kernel phi is now a map from omega times omega into LW. So the space of these linear and bounded operators. And we have still these two conditions. The first one is that somehow each of these elements is in H. Now, compared to, so this is the scalar valued version that we had earlier, and it's a special case of this one. We now have an alpha here. Why is that? Well, the phi is a map from W to W. So we need an element alpha in W to have, again, an element with values in W. So this needs to be in the Hilbert space, argument in omega, and the map should have values in W. And this is the reproducing kernel property. Again, we have to have this inner product of f of x, which is a function with values in W, with alpha, again, in W. And this is the scalar product in W. And that can be reproduced by this quantity with the inner product in H omega. And you can see that a special case would be where W is R, and we get the scalar valued definition back. We need to say what the inner product in W in R is. This is just the normal product. And we can identify the set of all linear bounded operators from R to R just by R itself. And that's basically how we get these two properties earlier back, because the alpha would just be a number, basically. And this is just a product with alpha as well that we can take. But this is now kind of fit for purpose, because now W is just any Hilbert space. So it could in principle, and will in principle, now be the space of matrices or symmetric. The other thing we were interested in was what properties can we deduce of this kernel, and in particular, what's the Ries representative. So here, if we switch the order of x and y, we get the star in W. And if we want to look at the Ries representative, we need an orthonormal basis of W. But remember, W is just in our case, the space of symmetric matrices. So this is quite easy to find an orthonormal basis of that, which we'll do a little bit later. If we have an orthonormal basis of W, we can write the Ries representative of of lambda in this way. We have to expand along this basis here. And then it's basically, again, the lambda applies to the kernel, to one element of the kernel. So let's have a look at the proof of this property here. So first of all, we can write by the properties of the orthonormal basis, V lambda just expanded along the orthonormal basis here. And now we're just looking at this red term here and want to say this term here is the same as the term up here. Now we've proven our statement. And this proof is basically the same as earlier. So in the first step here, we're using the property of the Ries representative. So lambda has a Ries representative V lambda here. We can switch the order here, and then this is the reproducing kernel property again. With this knowledge of the Ries representative, we can now find an expression for our interpolation matrix, Aij, which was given by lambda I applied to the Ries representative of lambda j. And just using this expression for the Ries representative, we get this formula here. So that's, again, a relatively easy way to calculate this matrix if we know the lambdas and obviously the kernel, and we need to know an orthonormal basis of W. But that's not very hard. For example, if W is the space of symmetric matrices, as it will be later, then we first of all define the matrix matrices E nu mu nu, which just has a 1 at this particular entry. This would be a basis of Rn times n in orthonormal basis. If we look at the symmetric matrices, then we have the following basis. First of all, we have the one where there's a 1 on one element of the diagonal. That's this one. And then we need a symmetric matrix where 1 over square root of 2 is on both elements of the diagonal. And these are n times n plus 1 over 2 elements. And they form an orthonormal basis with a standard inner product, obviously, in the matrix space. Right, so now we have all tools together to actually solve the problem of an optimal recovery of a matrix-valued function with values in either matrices, general form, or symmetric matrices, if we're given elements in the dual space. Now, also we obviously need to have an example of a kernel. And the good thing is that if we know a kernel in a scalar valued RKHS, then we can automatically easily find a kernel in the matrix valued space. First of all, let's remind ourselves what a kernel actually is now. A kernel, so phi of x, y, is a map from matrices to matrices. Yeah, so we apply phi to a matrix alpha, and that again is a matrix with coefficients I, j. We can express this by fixing phi x, y with indices I, j, k, l, where I, j, k, l go from 1 to n. So it's a tensor here. And the lemma is, if small phi is a kernel of the scalar valued RKHS, and we need this so that it's actually an RKHS. So this is a Sobolev space, I should say. Then the matrix valued and also the symmetric matrix valued RKHSs, well, Sobolev spaces are reproducing kernel Hilbert spaces, and the kernel is just given by that phi, which is a scalar valued function, and the IJKL are just given by these deltas. So as usual, delta ik is 1 if I is equal to k and 0 otherwise. So we have an easy way, and we can use phi, small phi here as the Wendland function for the scalar valued Sobolev space, and then that gives us a kernel for the matrix valued Sobolev space in this one. Right, now I was saying earlier, our optimal recovery problem can be kind of a normal interpolation problem, a classical one, or it could represent the interpolation of certain elements in a linear PDE. So we are interested in linear PDEs. So we are interested in a differential operator mapping matrix valued functions to matrix valued functions, but kind of we start smoother, and it's a differential operator of order m. So this sigma here is tau plus m, so we lose an order m. And we're looking at differential operators of this form. So they are of order m, so our differential here, which is applied component-wise in this matrix valued, so m of x is a matrix, and the d alpha is understood to be applied to each component. So this is again a matrix, alpha goes up to order m, and the c alpha is in the space of linear operators, so mapping this matrix to another matrix, and it's such that if we start with m in with smoothness sigma, then we map it to tau. We will see an example of such an operator later, which is our application, but the theory obviously holds for general orders here. Now, we need to be careful that the points that we choose later, so our, let me probably say what our lambdas are. So our lambdas are operators in the dual space is we apply the differential operator to m, evaluate at a certain point xk, and then we just look at all the components ij, because this will be symmetric I is small or equal to j. But basically we're looking at this differential operator at certain points xk. And we need to make sure that these points are no singular points to make sure that these lambdas in the end are linearly independent. So the extreme case of a singular point would be that this is here just 0. That obviously shouldn't happen. But what we actually need to exclude are points where C alpha at this point is not invertible for all alpha, because that will lead to problems with the linear independence. So if all these points are no singular points and we define our lambdas in this way, then they are all in the dual space and they are all linearly independent, and we can apply all the theory. So basically later for our application, we need to make sure that our differential operator is of this form, and we only choose no non-singular points and define our lambdas in the dual space in this way. Basically, these points are points where our PDE will be satisfied later, and if we fill it with more and more points, then we obtain error estimates that our solution will be close to the true solution of the PDE we're trying to approximate. Right. These error estimates, we will discuss these in the general setting here, and they all depend on the error estimates in the scalar case, and that in turn depends all on this theorem by Narkowicz, Ward, and Wendland from 2006, which is a very general theorem and works like that. It's basically, we're looking at a function u that has many zeros. So the u will later be the difference of true solution minus approximation. And that will have lots of zeros because we interpolate something. So we just need to know that this function u has a lot of zeros in the sense that it's 0 at these finitely many points x1 to xn. And if we know that, then there's a constant that we can estimate the L infinity norm of u by a constant times the h sigma norm of u times this quantity. The quantity h is the fill distance of the points x in omega. It basically measures how dense these points are distributed in omega, and the more points, basically, we have in omega, the smaller this h here. And the order is sigma minus d over 2. So the sigma is how smooth our u will be. So the smoother our u, the better the approximation. The other thing we need is a technical condition that omega as a bounded domain has a Lipschitz continuous boundary. So this is the tool we're going to use to deduce our error estimates. First of all, let's define the setting. Again, omega is a bounded domain. We now need this Lipschitz continuous boundary. And both sigma and tau are larger than d over 2. This is the differential operator as above. And we have points, these points x1 to xn in omega, and they can't be singular points of f. We define lambda as above as well, and then s denotes the optimal recovery of m, which we know is unique. And then we know that f of m minus f of s, so this is actually the quantity that was u in the previous slide here, that has lots of zeros because we interpolate f of m by f of s somehow. So that this will be 0 at lots of points, mainly, basically at all the points here, x1 to xn. And the L infinity norm of this quantity, which is again a matrix actually, matrix valued function, is bounded by this quantity here. And basically it's just the previous error estimate, but they use component ones. So just to recap, this error here is small if, well, first of all, we need to ensure that our solution here, that's m, is smooth enough. And then if the fill distance here is small, then this here will, we have a bound here going to 0. Let me just also point out the slight disadvantage of these kind of estimates. If we don't know m, then obviously we don't know this constant, and we don't know this constant either, but we basically know something about the order of approximation here that we get. Right, let me summarize this first part that was about this kernel-based methods before we then actually come to the application in dynamic systems. Well, we come back to certain elements here, but this the general setting. So we were looking at a linear differential operator in a subgroup space with matrix values. So mapping H sigma from omega to the matrices to H tau of order m usually. So the sigma is tau plus m. In the end, what we want to do, I probably haven't said that yet, is we want to solve a PDE of this form. So linear differential operator applied to m at point x is a given matrix valued function. So R is given, we know the differential operator, and we want to find the solution m of this equation. And what we will do is we choose points in omega. So this should hold for all x in omega. We choose points in omega, which are no singular points of f, and we want to solve the optimal recovery problem of the form f of s is R at all the points x1 to xn. So basically we want to satisfy our PDE at these finitely many points. We set up the matrix as we've done. We solve this. The size of the matrix is n, which is the number of points here, times, and this is the number of variables for a symmetric n times n matrix. We solve that in our reproducing kernel Hilbert space. We get our solution, and we have these error estimates of the error f of m minus f of s in the whole of omega. Yeah, so at these points, obviously, this error is 0, but in between there, we get an error estimates in terms of the fill distance of points x in omega. So basically, the more points we put in, the smaller the error, and it will converge to 0. So the next section gives us an example for this kind of problem, where we want to really solve a matrix-valued equation f of m is R that will define a so-called contraction metric. And we'll see in the next section what that means dynamically and why this is important. Right, let's go to the next section, which is a contraction metric. So this is a dynamic systems part, and we're looking at an ODE of a general autonomous ODE of this form. X dot is f of x with an initial value x of 0 is psi. F will be C sigma. Sigma needs to be at least 1. We will have certain conditions on sigma later, which I will explain. But if it's at least C1 and it's actually defined for all positive times, then we can define a dynamical system, and we call the flow operator ST psi, which is the solution of this system at time t and starting point psi. And then obviously in dynamic systems, there are certain solutions that are special. So just to remind everyone about the definition of an equilibrium point, which is a point where the right-hand side is 0. And the basin of attraction of such a point would be all the starting points where the solution starting at psi would converge to the equilibrium point as time goes to infinity. It's relatively easy to find equilibria just by at least numerically solving this equation here. It's a lot more difficult to find the basin of attraction because we really would need to find solutions or approximate solutions here. Another special solution obviously are periodic orbits, solutions where you start at x and after time capital T you come back to the point x. And again, we would be interested in the basin of attraction in the sense that the distance of the solution starting at psi to the set omega converges to 0. So we're looking at a differential equation, an ODE of this type, and we're interested in finding the basin of attraction of an equilibrium or of a periodic orbit. Methods to do that are well, there are plenty. One is dividing the phase space into cells, and then looking at the mapping between these different cells and working out where cells are mapped, and that's a powerful method to find bases of attraction. You could look at the boundary of bases of attraction, which would be invariant manifold, and detect those. You could try to find a Lyapunov function, which somehow measures the distance to an attractor in some way. The disadvantage would be you need to know where the attractor is, and especially for periodic orbits, that could be done probably only numerically. And we are going to look at contraction metrics, which is not the distance to an attractor, but just measures the distance between adjacent solutions. So it's a local criterion, and the attractor, so periodic orbit or equilibrium, isn't a special point. It's basically, as I said, a local criterion. And there's a lot of literature going back to Borg in the 60s that deals with these concepts. The advantages of a contraction metric is it's a local criterion, and I'm going to explain exactly how that works. You don't need to know any information about position or even existence of an attractor, but in turn, if this criterion is satisfied, it will show the existence and uniqueness of a certain attractor, so either equilibrium or periodic orbit, and it also gives you information about the basin of attraction of this attractor, and it's robust under perturbations of the system. So even if you perturb your system and perturb your equilibrium point or your periodic orbit, it will still be a valid contraction metric, and we will be looking at that later. Now, let me try to explain this criterion for a periodic orbit, because it's, well, first of all, it's easier to see, and then it's also more interesting for this one. We will later focus more on equilibria, mainly because it's less technical, but for this one, let me explain it for a periodic orbit. So assume you have a point x here, and your solution through x will go in direction f of x, so tangential to this line here. And then what we want to know is what happens if you are close, if you start at the point x plus delta v. Delta is supposed to be small, so we are near x, and v is kind of the direction in which we look for adjacent points. And we will assume that v is perpendicular on f. So basically, we're looking at solutions through x that go this way, and solutions through x plus delta v that will go in direction f of x plus delta v. And the question is basically, are they approaching each other like this? So the distance here will contract, or will this arrow point away somehow? So will the distance increase? We're interested in contraction, so the f pointing this direction. What's an analytical criterion for this picture to happen? So as I said, we assume v to be perpendicular on f, and with norm 1, Euclidean norm 1. So if this goes downwards, then the scalar product of v, so this v times f of x plus delta v, should be negative. Now, if delta is small, this scalar product here is approximately this here, so we can use Taylor expansion on f. It's f of x plus delta df Jacobian of f at x times v. Now, we assume that v and f are perpendicular, so this term is actually 0. So what's left is just v transposed dfx v times delta. Delta is positive and small, so we're looking at this quantity, and this quantity, the sign of this quantity will tell us if it's negative, then the arrow goes down, so it's contracting. If it's positive, it will go that way. And if it's 0, we probably need higher order. So we want this quantity to be negative. Now this would tell us if this is negative trajectories through x and x plus delta v, where d is positive and small, they will approach each other. Now, what we really want is that trajectories in every direction perpendicular to f are contracting. So basically, we take the maximum over all these v. So v should be perpendicular on f and norm 1. If the maximum of all these quantities is still negative, and that's what we call L of x, then trajectories to x and adjacent points, perpendicular to f, I should say, they all approach each other. So that's the contraction condition that will be appear in the next theorem. So here's the theorem, as I said, going back to Borg some 60 years ago. This L of p is negative, or bounded by a negative constant even, for all p in a certain set. That's the condition I explained on the previous slide. Now we also need to know something about the set K. So this contraction holds in a set K. The set K needs to be non-empty, includes no equilibria, is positively invariant. So basically, if you start in there, you stay in there for all positive times. It's compact and connected. If you have these conditions, which basically tell you, as I said, this is the local criterion. This obviously is a little bit global as well. You have some information about positive invariance, but basically it's just along the boundary. If you have these two ingredients, then you can conclude existence and uniqueness of a periodic orbit in K, which is exponentially asymptotically stable. And this minus nu is an upper bound of the real parts of the non-trivial flow K exponents. So there's 1, 0, but the other ones kind of tell you how something about the attraction. And the set K is in the basin of attraction of this periodic orbit. Yeah, so that's quite a powerful result. The next question is somehow, is this condition necessary as well? And the answer is no. And you can see this in this little figure here. So the black line here is omega. It's an exponentially asymptotically stable periodic orbit. But if you compute this L, this function L, then you can see it's positive here, it's negative here, and then positive in here again. So what does it mean to be negative? Here it's negative, so an adjacent solution, blue here, the distance here will contract. Here it's positive, so it will expand the distance, and here it's going to be negative again, it will contract more. So you have some areas along the periodic orbit where it's contracting, expanding, contracting, but kind of if you go overall, you can clearly see the distance here is contracting. This L of x being negative would mean it's contracting everywhere. So if you have non-monotone approach of adjacent solution, then this criterion won't hold, but it's still an exponentially stable orbit. So the idea is, well, we've just used somehow the Euclidean metric, and that's probably not appropriate to have contraction everywhere. The question is, can we find a metric that's contracting everywhere just by finding the right metric? And the answer is yes, but first of all, we need to define what we mean by metric. But that's kind of the motivation why we need the appropriate metric to capture this feature of the system that adjacent solutions are getting nearer and nearer. So in this context, the Riemannian metric is just a matrix-valued function which defines a point-dependent scalar product. So we basically want a scalar product between vectors v and w in Rn. That's defined by this expression here. If m of x is the identity matrix, then it's the usual Euclidean metric, but here it's a point-dependent scalar product. And m of x needs to be a symmetric matrix, which is also positive definite for each x. So that's the motivation to define this matrix-valued function as a Riemannian metric. It's a function from Rn to the symmetric matrices which are also positive definite. And it should be a C1 function to define a derivative in the next definition. So we define the orbital derivative. Now, for a function, a scalar valued function, the orbital derivative is just the derivative of this function along solutions of our differential equation. So you can see this here. It's v along a solution x of t of our differential equation. What's the time derivative? Using the chain rule, we can see that that's the gradient of v times x dot, and x dot is f. And that's our definition of the orbital derivative, which I will denote by a dash. Now, for a matrix-valued function, the definition is exactly the same, but component-wise. So a matrix-valued function will also have an orbital derivative, and that's again in matrix-valued functions where every component we look at the orbital derivative. That's why we want a C1 function, so that this is well defined. Right, so now what we can do is now we lift, let me just go back, this theorem here, which, as I said, actually depends, as I showed you in this picture, on the Euclidean metric. So that's here. We'll generalize this to a general Riemannian metric. So the new elements are just in red here. K has the same properties here, but the function L here is now dependent on the metric M. So you can see this, first of all, here. We take the maximum of, this is basically V as norm 1, but in this new point-dependent scalar product. And it's also perpendicular on F, again, with respect to this new scalar product with M in here. And this is the corresponding formula now taking M into account. If you think about M being just the identity matrix, we're back to the previous theorem, because the derivative of the identity matrix here would be 0, and here this would just be df plus df transposed over 2. So that's exactly what we had earlier. So this is a more general version of the previous theorem. It's a sufficient condition if you have the right Riemannian metric that with respect to which the Lm is strictly negative, then you have the exact same conclusion, existence and uniqueness of a periodic orbit. You have a bound, again, this bound on Lm as a bound on the Fouquet exponents, and K is in the base of a transition. Now, this is a more general sufficient condition, and the question is this now, can we satisfy this always if we find the appropriate Riemannian metric? So is this necessary? And the answer is yes now. And I will show you one converse result and another one later. So the first one here is if we have an exponentially asymptotically stable periodic orbit and we have a bound, this is the largest real part of non-trivial Fouquet exponents, and we have a compact subset of the basin of attraction, then in this compact subset, we can find a Riemannian metric so that Lm is bounded by minus nu. So we need basically a little epsilon. It's something that's strictly larger than our bound here. And the proof is locally, we can find this M by Fouquet theory, and then we match it globally with a Lyapunov function to find such a Riemannian metric that satisfies our conditions. Now, it would be really nice to find M. Yeah, this theorem tells us if we have M that satisfies all these conditions, we gain a lot of information, especially that K is in the base of attraction. But this theorem tells us there is an M out there, but to find it, at least the proof suggests we would need to know all, basically the solutions of our ODE. Is there a way to find a function M that satisfies these conditions? Now, before we go to this, pursue this question, let's go to the case of an equilibrium point. As I said, we will now kind of focus on the equilibrium case because it's simpler in terms of computation and technicalities. Recently, I've also actually, well, basically, I've done the research on this first, and I'll present you the results in this talk. There's also now a paper on the periodic case as well, if you're interested, but I won't talk much about it anymore in this talk. So the corresponding theorem to this one here, in the case of this was the one for a periodic orbit. Now, if we want to find an equilibrium point, the difference here is, first of all, the set K, you don't exclude K having an equilibrium point, because that's what you actually want to find in the end. So K is just supposed to be positively invariant, compact, and connected. We have again a Riemannian metric as defined earlier. And now the difference of this function Lm is, sorry, and this should have been the same L as here. This L of xv is the same as previously, but we now only take the maximum with norm 1 compared to here, the one where we only look at directions v that are perpendicular on F. Yeah, so here we basically look at every direction v, every adjacent point. So the contraction happens in all directions. For periodic orbits, it can't happen in direction of the flow, because on the periodic orbit, there won't be any contraction along the flow on the periodic orbit. So we have somehow n-1 dimensional space where we have this, where we check these contractions. To get to an equilibrium point, we have contractions in all directions. So that's kind of the new different feature here. So if this is satisfied with this maximum over all directions v, which are norm 1, then we have the following result. We have existence uniqueness of an exponentially stable equilibrium point. The minus nu here is an upper bound of the real parts of the eigenvalues of df. So basically, again, the attraction to this equilibrium point, and K is in the basin of attraction. And the converse theorem is very similar. If you have an exponentially asymptotically stable equilibrium point, then you will always be able to find your Riemannian metric with this property that it's negative. Again, the minus nu is strictly larger than the largest real part here, and we focus on a compact subset. But again, this doesn't really help us to compute it. So here's a second converse theorem that's actually more helpful to compute, and it links back to the first part of the talk. So let's have a look at this one. So again, we assume we know there's an exponentially asymptotically stable equilibrium point, and C is a matrix that's positive definite that comes up here. Then this M, which will be our Riemannian contraction metric, is a solution of this matrix valued equation. And you will recognize this part, at least, I will go back, is exactly this, this expression here. Yeah, and in the end, we want this function here to be negative, the maximum. And what we want somehow is that this matrix here is a negative definite matrix for all x. And that is, as it turns out, equivalent to this being negative. Yeah, so we focus, instead of an inequality, we actually can prescribe what kind of negative definite matrix this here is and get a solution for n. Yeah, so let me get back to this theorem. We can say this is equal to some given positive definite matrix, C. So every C, so C is positive definite, minus C is obviously negative definite. Any negative definite matrix here will give us a unique solution for this matrix equation, M. And this M is a Riemannian contraction metric. what I mean by that is that this Lm is negative and m is positive definite. Yeah, so if we're given x naught stable equilibrium point, given the right-hand side here, then there's a unique solution for this matrix equation. The other thing to note is it's actually defined on the whole basin of attraction, not just a compact subset. It's a contraction metric. As I said, it means that the Lm is negative, which you can see from here anyway, and that m itself is positive definite for each x. Have a little look at the smoothness. So if f is c sigma, then m is c sigma minus 1. So we lose 1 degree of smoothness, and that's why sigma needs to be at least 2. So we have at least 1 here. And the proof, which is a little bit technical, is basically based on this observation. We can define m, the solution, in this form. So it's the integral from 0 to infinity along solutions of phi transpose c phi, where C is this matrix, and phi is the fundamental matrix solution of the first variation equation along solutions starting in X. Yeah, so this is a matrix itself, and you can see that phi in general will have 1 degree of smoothness left because you have df here. So this is only c sigma minus 1. And the technical part of the theorem is basically check that this is smooth enough and it satisfies this. Now, at first sight, it seems that we haven't gained a lot. So this is, you could say, quite a complicated, it's a matrix valued PDE, as you see here. It's linear in M, but it's probably difficult to solve, you would say. Now, with the knowledge of our first part, we have now a theory to actually solve this. So that's what we are going to do in the third part. But before we go to that third part, let me just give you a glimpse of what this equation actually means in a very simple case and what it is related to. So the simplest case you can think of is if the differential equation here is a linear equation. So if f of x is linear, f of x is just ax, and then the matrix equation here, we also look at a constant solution, m of x is independent of x, so it's just m naught, becomes something called the Lyapunov equation. So df is just a, m is just m naught, same here, and if m is constant, then the derivative here is 0. This is known as the Lyapunov equation, and again, so a is given, c is given, the question is there a solution m naught, and what do we know about that? Well, the Lyapunov equation has a unique solution, m naught, which is given by this formula here. If a is, I should say, if a is negative definite, which basically is equivalent to x being, 0 being an exponentially stable equilibrium point. And this here is precisely our formula in this specific case, because phi t x, we're looking at the fundamental matrix solution of the first variation equation. So the first variation equation in this case is y dot is, well, this is just a, y dot is a y, and the solution is obviously the exponential at. So in this case, this formula becomes the well-known formula for the solution of the Lyapunov equation. Why is it called Lyapunov equation? Well, this m naught, the solution, if you use it as a quadratic form here, x transpose m naught x, that's the kind of the standard quadratic form Lyapunov function for this linear system. And for our application for the contraction metric, m of x being the constant matrix valued functions, m naught is a contraction metric in that sense. Yeah, so that's the illustration of this this theorem in the simplest case where f is linear. Obviously, this is the in general, it's non-linear, and then you have this more general. Right. Now, to the third part. So in the first part, we've seen how to use kernel methods to solve matrix-valued PDEs. In the second part, we've seen a dynamical systems problem where we're interested in solving matrix-valued PDEs because we want to find a contraction metric. And now the third part, we link these two together. So let's recap what our problem, dynamical systems problem was. We want to find a matrix-valued function M with values in the symmetric matrices so that M of x for all x is positive definite, but this quantity here is negative definite. Yeah, so this was that M really is defines a scalar product. It needs to be positive definite, and this corresponds to the contraction of solutions with respect to this matrix. Now, this is a problem that has been studied in different contexts, and these are some numerical construction methods that people have used. So the first one is, as you see here, so this just means positive definite, negative definite. These are linear matrix inequalities. So there's a method called sum of squares that can be used to solve linear matrix inequalities. For polynomial systems, and also the M will be component-wise a polynomial. So that's one way of solving these. You need to know, or you need to determine the maximal degree of polynomials, so that has its limitations there. Then a different method that was used is continuous piecewise affine functions. So for this method, you take your set K, triangulate it, and try to find M as a function that's affine on each triangle or simplex of your triangulation. And basically, you just need to fix the values at the vertices of your triangulation, and these conditions become constraints of a semi-definite optimization problem. So I've done that together with Hafstein. Again, the drawback is somehow that these, if you have a very fine triangulation, which you need to get good results, then these problems are quite hard to solve numerically. So you can only get so far. A more successful method is the one I want to present today, using kernel methods or meshless collocation that we've seen earlier, and that's the method I've developed with Holger Wendland, and we are going to kind of apply to this system now, this problem. So our linear differential operator that I called Fm in the first part is now this specific operator of order 1. Yeah, so order 1 because we have first order derivatives here of M. And it's linear in M, as you can see. F has no singular points actually in the whole basin of attraction. I show this later. That's, as you remember, we need to ensure that our points, our collocation points that we use are no singular points. What we want to do is we want to approximate a matrix valued solution. Fm of x is minus c with a given matrix C by approximation S. So I will denote M as the solution of this equation, which we know exists, and S as an approximation. And we know already to practically do this, we just need to set up a system of linear equations for the coefficients, solve that, and thus find the optimal recovery of this problem, given a certain amount of collocation points. And we know the matrix equation will be satisfied exactly at the collocation points, and everywhere else in K we have these error estimates. And remember that our error estimates are in terms of f of m. So we had this error estimate f of m minus f of s. The L infinity norm is bounded by this quantity, well, basically treating this m and c as a constant. And this here is the fill distance, and that will go to 0. Now, what we also will need, so basically that will tell us if f of m is negative definite, then f of s is negative definite. This is small enough. So that's one thing, yeah, because we wanted f of s, or yeah, this is f of m, this should be negative definite. But we also need that m, or our approximation s actually, is positive definite. And to do that, we have another estimate that, again, we will see later. The difference between m and s is also bounded. And it's actually bounded by this quantity times a constant. Again, there's a little catch in here that we'll discuss later. But these two error estimates will show that s is positive definite because m is, and f of s is negative definite because f of m is, if the collocation points are dense enough. Right, now let's basically go through these points that I said we will see later. We have no singular points, and we have this error estimate. First of all, let's look at the singular points. So f of m is given by this quantity. This is m dash, just spelled out a little bit more so we can see what the lemma will tell us. The first thing to note is if m is a symmetric matrix, then also f of m is a symmetric matrix, which can be clearly seen. And then we can write f of m in this form as a differential operator of order 1. C naught are the contributions of where just m comes in. So it's these two terms here. And C ej are the first order contributions where the derivative of m comes in. And we can see all points are non-singular because where either C naught or one of the CEIs must be invertible. If f of x is not 0, which means we're not in an equilibrium point, then clearly f is non-zero, so one of these must be invertible. If we are in an equilibrium point, or the equilibrium point, I should probably better say, then df has only eigenvalues with negative real part. That's the we're using here that we have an exponentially stable equilibrium point. And then the question is, does this equal to a matrix C? Is this invertible? And this is again the Lyapunov equation that we've seen earlier, with df of x being a matrix with only negative real part eigenvalues. And that has a unique solution. So this operator mapping mapping m to c is invertible. C naught is injected. So in A of x naught, we have no singular points at all. The second point I wanted to talk about briefly is this error estimate of m minus s depending on f of m minus f of s. And let's put it in a different context. So we look at this matrix equation again. The right-hand side now can also depend on x. That's actually not a big generalization. And we look at two different right-hand sides, Ci, so C1 and C2. And for each of these right-hand sides, there's a unique solution to this matrix equation. And it's given by this formula, which is the same formula as before. This dependency on x translates into the dependency on x here along solutions in this formula. Now, let's assume we are in a compact set K, and then we can see that the difference of these two solutions can be bounded by the difference of the two right-hand sides. Let's see how that goes. It's basically just this formula. So m1 minus m2, we can write as the difference here of these two formulas. The phi's are obviously the same, so that translates into a difference of C1 minus C2 with its norm. Now we're using that C1 minus C2. Remember that this is the integral along solutions. So it's not enough to stay in K. We need the positive orbit. So this is we're starting in K and following the solutions for all positive times. So that's why we need the bound of C1 minus C2 in the positive orbit of k here. We take the maximum here out, and then this here is exponentially decreasing. So this is just a constant independent actually of where we started. It's a compact set. So we have this constant here. And remember, the C's, if we go back here, were the right-hand side. So these right-hand sides are f of m minus f of s, and these are the solutions. Now this looks slightly worrying. However, if k is a positively invariant set, then these two are actually the same. They're compact. If not, and you will probably see that in some of the examples, you need this bound, and basically that you have a good approximation in a slightly larger set than what you get on the error bound here. We'll see that. Right. Now finally to the last section where we can see some examples, also highlighting one of the advantages of a contraction metric, which is that it's robust with respect to perturbations. Let's start with a very simple example where we can also look a little bit at error estimates. So this is a linear example, very simple example with a stable equilibrium point. We take these points, 1,600 points, and the linear system is a matrix of this form because it's number of points times the number of degrees of freedom for a symmetric matrix, so 3 in this case, in a 2x2 matrix. As kernel, we take this Wendland function, and it's a scaled one, so we have this constant c in here. And these are the results. So what we plot here in this figure is, we want to know that f of s is negative. So s is our approximation. F of s is what tells us about the contraction. So f of s should be negative definite. Here we look at the trace, which should be negative. And here we look at minus the determinant, which should be negative in a 2x2 matrix. So if both of these functions are negative, then f of s is negative definite. And you can see that it is negative definite apart from an area at the boundary. I'll show you another figure where we see this more clearly. Now for s, the approximation itself, we need that s is positive definite. So we look at the trace and the determinant. They both have to be positive. And you can see they are positive in the whole area that we look at here. So here is another figure showing these results. You can here see the collocation points as dots. You can see in red and green where the trace or determinant of f of s violate basically the sign condition. So and you can see it obviously happens in between these collocation points. At the collocation points, everything must be fine. But you can see it often happens near the boundary. We would need more collocation points to get this to the right sign. And then we see a representation of what S actually means. So S measures the distance. It displays a metric. So somehow a good way of showing this metric is a curve of equal distance around a point. So that at this point x, we've shown a curve of equal distance with respect to this metric. If it was, if s of x would be the identity, these would be circles, and these are ellipses. You can see though that actually they are all the same, look the same for all points x. So it seems that this solution here is not really dependent on x. And that is somehow to be expected because I explained earlier that the solution of f of m is equal to y for a linear case is constant. We've actually computed that earlier, and it's, let me just go back to this slide. If the linear system is, if the system is linear, then the solution m naught is the solution of this Lyapunov equation. which is the one I've solved here. So that's the solution. So that should represent S. So if S is a good approximation, it should be very close to this constant matrix. The other good thing is that now we have actually the solution in explicit form, so we can actually see what the error is, at least on a very fine grid. So what we did to see what the L infinity error is, we checked it on a very fine grid, and we did this for various fill distances, because remember that the error estimate, let me show you the error estimate again. The error estimate, oh, sorry, where is it? The error estimate here depends on the fill distance. So we basically look at different fill distance, treat the C and M here as a constant, and want to see whether it follows the order here that's given by Torm minus D over 2. And the results are given on the next slide. So this is the error of f of s minus f of m, and we use different alphas. The alphas correspond to smaller and smaller fill distances by a factor of 2. So the error here decreases, which is obviously nice. And to check whether this order of the error estimate is right, we divide the error with alpha 1/2 by the error of alpha 1/4, this by that, and so on. So we get these ratios, and the predicted ratio would be 2 to the power of 3.5 with a torque given by the Wendland function. And you can see that it's actually even slightly better here at the end than the 11 predicted here. And we can do the same with the difference not of f of s, but s minus m. And we saw the error, we could estimate this also by a constant times this error. So it should be of the same order here. The error here actually becomes smaller very quickly, and you can see that the convergence rate is actually a lot better than predicted. Right, now we go for a nonlinear example. We take the van der Pol example, which in the original version has a stable periodic orbit. We reverse the time, so the boundary of the basin of attraction is an unstable periodic orbit, and we have an equilibrium at the origin, and we are interested in the basin of attraction of that, which is somewhere an area of this shape. Now, here we see, now this time I've basically just plotted the right sign of f of s somehow. So if the sign of the trace minus the sign of the determinant is -2, that's the error down here, then that's contracting, so f of s is negative definite. And the same here for s, if the sign of the trace plus the sign of the determinant is +2, then s is positive definite. Or in this picture, I'm showing basically these two together. Here are my collocation points. In red, you see where f of s has the wrong sign, and it clearly has the right sign where my collocation points are, because that's what I'm approximating. And in blue, you see where s is not positive definite, so that's actually an area much further outside. So all the area here is fine. It's a contraction metric here. And here I display how this contraction metric S looks like, again, by curves of equal distance. And you can see that these ellipses turn round depending on X. So this clearly does depend on the point X. One aspect I said earlier that is an advantage of these contraction metrics is that if you perturb your system, the contraction metric still remains a contraction metric. And that even applies if you perturb the system so that the equilibrium point changes. So here is the same equation as before, plus an epsilon where we chose epsilon be 0.1. And you can clearly see that the equilibrium point is perturbed as well. So it's not 0, 0 anymore. What we've done now is we haven't kind of taken this system and computed an appropriate contraction metric for this system, but to highlight the fact that it's robust with respect to perturbations, we've taken the contraction metric for the unperturbed system, so basically this one here, and checked, is it still a contraction metric for the perturbed system? So basically we've taken S and we've just computed the sign of f of S and S again. Well, S itself is still positive, it's the same function. So the blue curve is the same as before. It's still positive definite where it was positive definite before. The only thing that has changed is F, because this F depends on the small f, our right-hand side, and that has changed now. So what we see here now is where you can clearly see the blue lines haven't changed. The red lines have changed. That's kind of the corresponding picture here. And you can now see that there are areas like these ones where there are collocation points, but f of S is not negative. That's because the collocation points satisfy a different equation than what we're checking here. Yeah, we are checking now this f of S where f is given by this perturbed system. But you can see still this area, in this area, it's still a valid contraction metric, even if it's even if it's a different system we are now studying. So that's very nice because you compute one metric and it's a valid contraction metric, at least in a large area for a perturbed system. That wouldn't work for a Lyapunov function, for example, which has to have certain properties at exactly the equilibrium point. If you move the equilibrium point, it fails to be a Lyapunov function. Here's a three-dimensional example given up there. Here you see where f of S is not negative definite, so it's a combination of all these conditions. Inside you see the collocation points. S is positive definite in the whole area described. So that's just to show a three-dimensional example, really. Right, so that brings us to the end of my talk. Thanks for your attention. Let me just summarize and then point you to some references if you're interested. So in the dynamical systems part, I've talked about a contraction metric. It's a local property of a system that the sign tells you whether the distance between adjacent trajectory contracts or expands with respect to this metric. And the challenge somehow is to find a metric that is contracting. Once you have found a contraction metric, you can determine an attractor, periodic orbit, or equilibrium. We've mostly now focused on the equilibrium, and its based on attraction. You don't need any information about the attractor. It's also robust with respect to perturbations. We've seen converse theorems that tell you if you have a certain type of attractor, then there exists a contraction metric. And we've also seen you can find converse theorems in terms of matrix valued PDEs, so that you need to approximate these and have we've seen a numerical construction method. I should point out that I've said it's an approximation, which is true. It's an approximation of one specific contraction metric. The good thing is, if we are close enough, if our error is small enough, then even the approximation that we've seen is a contraction metric. It's not exactly the contraction metric specified in this converse theorem, but it's a valid one. And because there are lots of contraction metrics, they just have to satisfy an inequality. We start from one that satisfies an equation, have one that's close enough, and that will give us a valid contraction metric satisfying an inequality. I've started with periodic orbits, and indeed the same method can be done and has now been done for periodic orbits. So there's also converse theorem with an equation for periodic orbits and a numerical construction method using the same kernel methods that I've described here. And another work that is being done as we speak, and we've published already some results of that, is kind of the next step. We've seen here methods, numerical construction method that construct these contraction metrics. What we've now done here is somehow check that they have the right sign in this area. This was done by just checking the conditions on a lot of points in between and hoping nothing goes wrong in between. And somehow we know if our field distance is small enough, then nothing can happen. We have these error estimates. The problem is we don't know anything about these constants here. So we don't know how small the field distance really has to be. It's more, if h is small enough, at some point it'll work. And to have kind of more quantitative error estimates, we have developed a verification method to really verify the definiteness. And we're using the CPA method that I spoke of earlier, but just as a verification. So it's, earlier I said you can use this method also to find a contraction metric. Here we're using it to check whether the metric we found here is valid. The idea is actually the same as finding one. So what we do is we take the metric here, have a very fine triangulation, and just take the values of our numerical construction that I've just described at the vertices, interpolate that, and the interpolated function, we can really easily verify the definiteness at these finitely many points. And this includes an inbuilt error estimate that the definiteness also holds on each, in the whole triangle. So that's a useful technique that we've developed earlier for Lyapunov functions and can be used also for this contraction metric and has already been useful for the equilibrium case. Let me finish with some references. Obviously, I put a lot more in the slides, and if you're interested in more, do contact me. The two red ones are the two papers on which most of the talk is based. This is more on the kernel theory, just with a little bit of applications in dynamic systems, and this is more on the application side to contraction metrics. And here are some related ones with me as a co-author. As I said, please do contact me for other references that you're interested in. And I hope you enjoyed the talk. Thank you very much for joining. And I hope you enjoyed the talk.